Hey everyone, this is Dr. Brian MacDonald, author of Practical Stress Analysis with Finite Elements. And this is the video number 9 in our series FEA101, which is an introduction to finite element analysis. And in this video, we're going to be discussing beam elements. So let's get right into it and just start talking about beams. So first of all, what are beams? Beams may be defined as slender members that are subject to transverse loading. And again, the transverse loading is the key point here. So typical examples are long horizontal members used in buildings and bridges, etc. So if we look at a typical cantilever problem, we have a long, slender member, okay, and it's subjected to transverse loading, so loading across its height or thickness there. And most of us will have done some kind of elementary study of beam analysis in university or something when we're looking at the early stages of an engineering or a science course. And we'll have done things like producing bending moment diagrams here in the bottom and shear force diagrams. So here we can see the typical results for a cantilever problem. Or also we have a simply supported problem here. So in this case, in the cantilever problem, one end is built into a wall and the other, the free end, supports a tip load. Here we've got two ends of the beam which are simply supported, and we have a load in the interior of the beam. And again, we get a very different bending moment and shear force diagram here compared to the cantilever problem. And we'll discuss this as we work our way through examining beam elements. Beams in finite element analysis tend to look like this. They just look like lines, but they behave like this. So whenever we define a beam element, we generally define its second moment of area, or its cross-section, or its cross-sectional area. And the shape of its cross-section is very important because this type of cross-section here, this I-beam, would be a lot more difficult to bend than if it was just a flat rectangle, for example. So again, if you were making a bridge yourself across a small stream, if you had a flat plank of wood, that would bend much easier when you walked across it than a piece of wood shaped in an I-beam like this. So being able to associate cross sections with beam elements is very, very important, and we've lots of different cross sections we use for different types of beams for different applications. So in terms of beam theory, then we have the Euler-Bernoulli beam bending equations, and these are essentially these equations here. So we have our first equation here, which says that the stress in the beam is a function of the bending moment, the second moment of area, and y. Y here is the distance from the neutral axis. Okay, so the neutral axis is normally going along the centroid of the element. So if we took the centroid of the beam cross section. So if we took the centroid here and linked up all the centroids all the way through, that would be our neutral axis. So what this equation is telling me here was if this beam was, let's say, for example, cantilever, let's say this end was held and this end had a load, that the distance y, so y from the neutral axis, has an effect on the stress. And what that means is that, for example, I would get a very high stress on the top and the bottom of the beam and a zero stress at the centroid of the beam, because as y increases, I'm moving away from the neutral axis. Then we have our constitutive equation, which basically relates stress to strain. So we can have strain is equal to stress over Young's modulus, or vice versa, stress is equal to Young's modulus times strain. And then finally we have an equation which relates deflection to bending moment. So here we have the second derivative of deflection. So deflection is movement in the vertical direction, up or down. M is the bending moment. E is the Young's modulus or elastic modulus for the material the beam is made of. And I is the second moment of area of the beam cross section. So again, if I have an I-beam, it's going to have a very, very different second moment of area to a cylinder or to a square or to a T-beam or an L-beam or something like that. So even if they're all the same height, they have very different I values. Again, a useful practical way to think of what I is, it's almost a measure of how mass is distributed from the centroid. So here if we look at this I-beam, there's a lot of mass up here which is far away from the centroid, whereas if we took something like a simple square or a solid circle, the mass is much closer to the centroid. So here this is why the I-beam is more difficult to bend, is because it has a higher I. Okay, so if we look at our strain energy then, going back to our minimum potential energy equation, we're looking at our strain energy term. We have, as usual, the strain energy is stress times strain. Okay, and in this case, we're talking about the area, so dA, and then that's multiplied by length along the beam. So x is length along the beam, A is the area. So first of all, we're integrating over the area and then also along the length of the beam as well, dx. So what we're going to try and do now is kind of replace that stress and strain with stuff that's more easily quantifiable. And for beams, what we're actually going to do is we're going to put in my all over I, where we have stress. And then if we look at strain, well, we see that strain is my divided by I divided by E. Okay, then we put those two things in, we get this term here. So we get a half m squared E all over I squared. Okay, so that's coming from m multiplied by m. So again, we're getting stress twice there. And the I squared again is coming as well because we have that twice and we've got the E underneath the line as well once. So we've got those two squared, we've one of those. And also the y is squared because that's turning up twice. So we have the y squared. Now y is the only one that actually depends on a, so we can take all of these out as a constant. So again, we'll know the bending moment based on the load that's applied to the beam. We'll know the Young's modulus or elastic modulus of the beam material, and we'll know the second moment of area of the cross section. So these will all be constants that we'll know. The only kind of unknown is this bit in here, the y squared dA. So the integration of y squared dA is effectively a statement of what the moment of inertia of the beam cross section is. It's a formal statement really of what I is. So we've got different formulas for calculating I for different sections. We've got our BD cubed over 12 for rectangular cross section and so on. But the integration of a y squared dA basically describes all of those equations. Okay, it's a definition of the second moment of area. So basically we can replace this here with I, and that I cancels one of the I squared below the line, and we're left with strain energy is a half m squared EI dx. So therefore then we can put that into our strain energy and say that we have a half the integration along the length of EI d2v squared dx squared to be squared. So what's happened there? We've taken that m squared there and we've replaced that in here. Okay, so that m squared over EI, okay, is this bit here. We've put that in there for that. Okay, and we have our EI outside here. Okay, so now our minimum potential energy equation can be rewritten like this. So again, we have the strain energy part, which is stress times strain, which we've rewritten down to, again, Young's modulus, a second moment of area, the second derivative of vertical displacement, and dx being the length along the beam. And this is going from 0 to L, which L is the length of the beam. And then we have the force terms. So normally we'd have body force, surface load, and point loads. They don't actually apply to beam problems. So in beams, we're looking at distributed loads. Okay, loads distributed over the length of the beam. We're looking at point loads that act in the vertical direction. And then we're looking at moments, which will act at certain points. So we've got distributed loads, which are integrated over the length they distribute over. We've got point loads, which are summed up. And we have got point moments, which are summed up as well. So let's just go through all of those terms again. So just for completeness, E is the elastic modulus of the beam material. I is the moment of inertia of the beam cross section about its neutral axis. V is the vertical deflection of the beam, so in there. FD is the distributed load per unit length of the beam. Fi is the point load applied at point I. Vi is the vertical deflection of the point I due to that load being applied. M is a moment applied at the point N. And V-N is the slope of the beam at the point N, which is often called the rotation of the beam as well. And this is also notated as theta n. Okay, so V-N is the derivative of deflection, which is slope. Okay, so again, if we have a moment applied at a point, it's going to cause the beam to bend at that point and change its slope at that point. Okay, so we get a curvature of the beam at that point. And again, x is length along the beam. So this one here is kind of important. We'll come back to this in a minute. Essentially, a moment causes a rotation or a change in slope, and that rotation we normally give theta n, but it can also be v-n or the first derivative of v. at the point N. Right, so let's first of all consider a simple one-dimensional beam element. The term one-dimensional is a bit arbitrary or disputed, because essentially it could be just called a simple beam element, which just bends in one direction. Again, sometimes people like to call it 1D because all the deformations are in the vertical direction, but it can bend and change its shape in the two-dimensional plane of the screen. So for example, this beam here its nodes can move up and down, but it can also change its slope at these nodes as well. So if it changed its slope, for example, it may bend down into more of a U shape or an N shape or something like that. So each node is free to move vertical, which is VI and VJ, and the slope of the element, in other words the curvature, can also be changed at each node, and that's given the symbol theta I and theta j. And again, remember, these thetas are the first derivative of deflection, V. So if we have a beam here that starts off in this configuration, okay, and we apply some loading to it, like in this case it's a distributed load, and it bends into that configuration there. If we were to look at a finite element model of that beam, and let's say we create 3 nodes, so we've got 2 beam elements. Okay, so what's happening there? So we start off with theta equal to 0 at node 1, V equal to 0 at node 2, and theta equal to 0 at node 3. So there's the slope here is 0, the deflection here is 0, and the deflection here is 0. And then after the loading, we find out that theta here is minus 0.35, and theta there is plus 0.35. So 0.35 radians is 20 degrees. So roughly we've got a 20-degree change in slope there. And this point here has moved down 0.05 meters. Okay, so that's kind of an illustration of the degrees of freedom of a beam element. We can change its slope at each node, and it can also vertically deflect at each node. So each element has 4 degrees of freedom. So the element displacement field will be a function of these degrees of freedom. So if we were to say the displacement of the beam element is going to be a function of VI theta I and VJ theta j, and that's essentially, again, the vertical displacement and rotation at each node. And because we have 2 nodes, that means we've got 4 of them. So we now need to determine shape functions for interpolating the displacement field V on an element that's defined on its natural coordinate system eta, with a node I having the coordinate eta is equal to -1, and node j having the coordinate eta j is equal to 1. So again, this is essentially what we did with truss elements as well, and we're going to do with all the other elements. We're going to use this natural coordinate system where one node has a coordinate of -1, another node has a coordinate of 1. And again, we do this because it makes the mathematics of solving these problems much, much easier. And it also means that every element is using the same set of coordinates, which makes it more efficient to reuse equations and so on. So these shape functions must not only consider nodal deflections, which we had before in the truss element, but now also nodal slopes, which is a new thing. The shape functions used must also ensure continuity of the dependent variable, which is the vertical displacement, and its derivative, slope, across element boundaries. So previously we only had to worry about having continuity of the dependent variable, which was, in the case of trusses, just deflection or displacement. Now we must also have the continuity of the derivative of the dependent variable across element boundaries. So the Hermite shape functions are conveniently used to satisfy nodal and slope continuity requirements, and they're essentially generally used to formulate beam finite elements. So if we take a look at the Hermite shape functions, then we have 4 of them. We have an SI and an SJ, and we have an SI theta and an SJ theta. So SI is taking care of the deflection at node I, SJ is taking care of the deflection at node J, SI theta and SJ theta are considering the rotations. So if we graph these, if we look at SI and SJ first, they have the same properties that we've looked at for previous shape functions. They have a value of 1 at their own node and a value of 0 at the other node. In this case, they're varying cubically. So this is a cubic equation. Okay, so this isn't a line or this isn't a quadratic curve, it's a cubic curve, it's doubly curved. So it's a little bit difficult to see because it's not very, very curved. But again, these are cubic equations. Again, if you look at the equation itself, you have an eta squared term multiplied by eta, so you'll end up with eta cubed terms in there. The slope shape functions are slightly different because they don't have a value of 1, they have a slope of 1. So SI theta has a slope of 1 at its own node, so it's basically starts off being 45 degrees and goes down to 0. And Sj theta has a slope of 1 at its own node, and the only way it can have that is to come from under the element. Okay, so you can see it starts off at 0, it gets more negative, and then starts sloping upwards. So I mean, it's important that it's a slope of 1 and not -1. Okay, so that's why it comes from underneath and goes back up again. And again, we have our usual equation here where we're relating the nodal deflections and rotations to the global displacement of the element via the shape functions. So again, this is exactly the same as we did with truss elements from before. Let's just take a quick look at the slope shape functions again. So again, there's a bit of an unusual thing. If I just jump back for 1 second, you'll notice that these are, 1/4, 1 minus eta squared, 2 plus eta. These ones are a little bit different. There's this L over 8. So the length of the element is coming in there. So just want to explain where that's coming from. So theta is equal to dv dx. Okay, it's the derivative of deflection. So v is deflection. We want to work in terms of eta. We don't want to work in terms of x. So we can use the chain rule and say, well, dv dx is dv d eta times d eta dx. And we know that d eta dx is L over 2. Because we have a relationship between x and eta, which is the same one that we had before for the one-dimensional truss. And we'll talk about that again in 1 second. So strictly speaking, this equation here, okay, would give you, instead of having SI VI plus SI theta theta, we'd have this L over 2 term. So for theta here, we'd have L over 2 dV d eta. Okay, so usually if you look up Hermite shape functions, you'll find that you have you'll have 1/4 1 minus eta squared eta plus 1 for the rotational shape function. But what we're going to do here is incorporate the L over 2. So incorporate this. So this essentially defines theta. We have this extra L over 2 here. We're going to incorporate that into our SI theta and SJ theta. Okay, you could do it the other way as well. You might find some books, what they do is they work the equation in this form here and keep the L over 2 out. At the end of the day, it doesn't matter which way you do it, you'll get the same answer as long as you are sure to include the L over 2. So that's why we have that L over 8. So again, just in case you're looking at this and wondering, well, why are these 1/4 and why are these have an L and it's divided by 8 and not by 4? That's why. So we have our equation for deflection of any point in the element is a function of the shape functions times the nodal displacements and slopes. We can put that into matrix form like this as we did before. So we've got a shape function matrix and a nodal displacement vector. So we have an expression for v in terms of shape functions. And now we can recall that the element strain energy is given by this we had before. And also we can say that, well, we're trying to look at this d2v dx squared term now. And we have dv d eta. And we want to kind of somehow relate that to this d2v dx squared. So we can say dv d eta is L over 2 dv dx. And again, that is coming from here. So our eta is 2xl minus 1. So we can say here then, just looking at relating this side of the equation to this side of the equation and rewriting, we have dv dx is 2 over L dv d eta. Okay, so we're trying to work out this here and get rid of these x's and just be working with eta. Okay, so that means that the second derivative of this then is going to be 4 over L squared d2v d eta squared. So again, there's that term there, and that's what we're after turning it into here. So now substituting v is equal to s times u in here gives me d2v dx squared is going to be 4 all over the length of the element squared d2su d eta squared. But the u isn't in terms of eta. U is just a list of nodal deflections and rotations. So it's just going to be a list of numbers. So that doesn't have to be taken account of in this derivative here. But s is in terms of eta, so that will have to be derived. So we've got an expression for d2v dx squared. But look, if you look in our strain energy here, that needs to be squared. So if we square that by each other, so we basically take this and multiply it by itself. And again, the u's are taken outside. The 16 all over L4 is taken outside, so that's 4 squared all over L squared to be squared. And then we have the transpose of d2s d eta squared multiplied by itself. So again, just clarifying what I was saying there, we're rewriting that there as this. So it's now been written in terms of eta and the shape function matrix. d2s d eta squared is going to be this here, because that we're going to get the derivative of our shape functions, the second derivative of our shape functions, and this is what they work out to be. Putting all this together then in the strain energy equation gives us this here. And as usual, what we're going to do is we're going to look at that there and we're going to compare that to our normal form of the strain energy equation, which is U, Ku. And if we look at that, we have U, U, and all this bit in the middle, and effectively means that that is K. Okay, so K is 4EI divided by the length cubed, second derivative of the shape function multiplied by itself and integrated between 1 and minus 1. And when we do that, we get the stiffness matrix for a simple beam element. And it's effectively a function of the elastic modulus, the second moment of area, the length of the element, and again in here we've got various combinations of the length of the element and the length of the element squared. So the next thing we need to be able to look at is the distributed force term. So again, what happens when we have a distributed force applied to the element? How do we distribute that force out to the nodes? So again, we use the shape functions. So again, we try and we replace our v here with s times u, and again we replace our dx with L all over 2 times d eta. So we get fd L over 2, again integrating the shape function between minus 1 and 1. And in that case, that tells us that the distributed force term is the transpose of this equation here, which basically means we take our distributed force that we want to apply to the element, multiply it by the length, and divide it by either 2 or 12 and apply that to the nodes. So for example, if we were applying it to node I, we'd have the distributed force multiplied by the length divided by 2 applied as a vertical force, and we'd have the distributed load times the length squared divided by 12 as applied as a change of slope. Okay, so as a moment. Then we can further go on and post-process our results. So in terms of dealing with beams, we're generally not interested in things like, stress and strain. We're more interested in bending moment and shear force. Of course, we do look at stress and strain as well, but most beam analysis, the first thing we're looking at is bending moment and shear force. We can work out our bending moment from this equation here. So the bending moment is equal to EI times the second derivative of displacement. And again, if we just put that in there, replace V times M with S times U, and get the second derivative of those, we end up with this equation here, which is a function again of elastic modulus, moment of area, length, and various combinations of the deflection and rotation of the nodes in that element. And then the shear force is basically the bending moment derived again, or like the third derivative of the bending moment, essentially. Sorry, third derivative of just deflection. And in this case, we just get the derivative of this equation in respect to eta, and we get this here. So that allows us to calculate our shear force. Okay, so as always, let's just try and pull all this together by looking at an example. So here we have a simple example where we have a beam that's cantilevered at one end. It's simply supported in the middle. It supports a vertical downward load of 40,000 newtons, and it supports a bending moment applied to the end or the tip of 20,000 newton meters. So what we're going to do is divide that into two beams. Okay, so our first beam will extend from the built-in end until to the simply supported point, and the next one will extend from the simply supported point to the end of the beam, and they're both 1 meter long. I'm going to call this point node 1, the simply supported point node 2, and the tip node 3. So again, 2 meter long beam. We're told the elastic modulus is 200 gigapascals. We're told that the second moment of area is 4 by 10 to the minus 6 meters to the power of 4. We're asked to calculate the deflection of the free end and the bending moment and shear force distribution. We're told that node 1 is fixed in all degrees of freedom, so it's built in. Node 2 is free to rotate but not move vertically, so that's what this simply supported one here means here. So it can basically go up and down, but it's not allowed to, it cannot move up and down, but it is allowed to change its slope. And node 3 can do whatever it wants. So using our previous equation, let's calculate the stiffness matrix for element number 1. So element number 1 has a Young's modulus of 200 gigapascals. It has a second moment of area of 4 by 10 to the minus 6. It's 1 meter long. So all the L's that would have been in here are multiplied by 1. So this is our stiffness matrix. So when we multiply all of this out, we get 8 by 10 to the power of 5. So what I've done here is I've integrated the degrees of freedom as to which they refer to in the stiffness matrix here. So you can see I have deflection at node 1, rotation at node 1, deflection at node 2, rotation at node 2, and the same down the side here, because element 1 refers to nodes 1 and node 2. I can do the same thing for element number 2, and you'll find out I get exactly the same stiffness matrix because it's got the same length and the same cross-sectional properties and material properties, but this time instead of having V1 theta 1, I have V2 theta 2, V3 theta 3 as it relates nodes 2 and node 3. So now what I can do is I can take those two equations and put them together. And in this case, I can start off with an empty matrix, and I can write V1 theta 1, V2 theta 2, V3 theta 3 across the top, and again down the side. And essentially, I just take the elements from each of these local stiffness matrices and put them into the global stiffness matrix. So for example, V1 is 12, and so on. And then if I get an interaction term, so let's say I go for V2, it's 12 from this matrix, and V2 is also 12 from this matrix, so I get 24 in there because both of them are contributing to V2. Okay, and the same, I work my way through the rest of the matrix like that. So there's my global stiffness matrix. We can now begin to assemble a global problem equation, which is K times U is equal to F. So in this case, there's my stiffness matrix I just worked out. Here, I have my degrees of freedom. So I have V1 theta 1, V2 theta 2, V3 theta 3. In each case, the vertical deflection and rotation of a node. And in the force column then, or the force vector, I have a shear force at node 1, a bending moment at node 1, and so on. So again, F1s is the shear or vertical load applied at node 1. F1m is the moment applied at node 1. V1 is going to be equal to 0, and theta is going to be equal to 0 in this case, as the beam is fixed rigidly at node 1. And V2 will be 0 as the beam is simply supported at node 2, so it means it can't move up and down at node 2, but it can change its slope. Okay, so essentially I'm going to have 0, 0, 0 in here, and only those three will be unknown. So if I go ahead and do that, I have 0, 0, 0. If I go and put my loads in, I've got minus 40,000 and I have 20,000. So again, remember I had a 40,000 load acting vertically downwards, and I had a 20,000 moment acting in the anti-clockwise direction, which we're going to consider positive. I put those in, I can solve this system of equations, so I only need to solve the bottom three lines. So in this case, I get the rotation of node 2 is minus 0.006 radians. The deflection of node 3, which is what I was asked for, is 0.0104 meters. The rotation at node 3 is minus 0.00625 radians. And then I can find out the bending moment in element 1 using the equation that we developed a while ago. So in this case, I have 0, 0. So again, I have 0, 0, 0, and theta 2, which is minus 0.00625. So I have 0, 0, 0, and there's my minus 0.0625. Multiply that out, and I get minus 5,003 eta plus 1. So the bending moment is dependent on eta. So it is dependent on the coordinate within the element. So if I set eta equal to minus 1, which is the coordinate of node 1, it tells me the bending moment is 10,000. If I set eta equal to 1, which is node 2, it tells me the bending moment is 20,000. Okay, similarly then for element number 2, I go through that same procedure. I put in all the values there. And again, these are the results. So remember, I had 0 for V2. I had this value for theta 2. I had this value for V3. And this value for theta 3. I put all those in, I get an equation which is again dependent on the value of eta. So at node 2, eta is equal to minus 20,000, more or less. And at node 3, eta is equal to roughly 20,000. And again, finally, I can go and work out the shear force. And again, it's just a case of putting in the unknown or sorry, the now known nodal values that I just worked out. And it tells me the shear force at node 1 is minus 30,000, and the shear force at node 2 is almost 40,000. So now what we're going to do is we're going to go into ANSYS Workbench and build the same problem and see what kind of results we get there and see how they compare to what we got here. Okay, so here I am in ANSYS Workbench and I've defined a beam model, which is essentially two lines. So there's the first line there, 1 meter long. There's the other line, 1 meter long. I have a fixed support on this point here. I have a remote displacement here, which basically only allows rotations about Z, which is the one I want because that's coming out of the page. I have a point load of minus 40,000 applied there, so you can see there. And I have a bending moment of 20,000 again applied here as well. In terms of meshing, I've literally meshed this into two beam elements, which is exactly what I have in the numerical analysis we just did there a second ago. As usual, the usual stuff. I have materials defined here as per the problem. Yeah, I think that's pretty much covers everything. So if we go and then look at our solution, so in terms of directional deformation, I just put a little probe in there. So that point doesn't move, that point doesn't move, and this point is minus 1.06 e to the minus 2. So again, if we just jump back to our solution here, you can see I've got minus 0.104, which is quite close to what we had. So we're 106, which isn't too far off. So now what I've done is I've already defined a path on this beam problem here, which is just along the length of the beam, and that allows me to get a shear and moment diagram. So here, again, at the bottom we have total displacement, and you can see that displacement is 0 at node 1, node 2, and node 3. It's in this case 1.06 instead of my 1.04. If I look at bending moment, it's going from 9,800 up to 20,000. And again, if you look at our solution, we had 10,000 going to 20,000, and again going up to 20,000 in element number 2. And finally, our shear force theoretically is 30,000, 40,000 roughly. So again, if we look at our shear force, we have 30,000 and 40,000. So we've gotten very, very close results to our hand calc FEA. Okay, so now what we're going to do is we're going to look at that same problem again. But this time we're going to remove the point loads on the tip and we're going to use a distributed load along element number 2. So exactly the same problem, all the same elastic modulus, cross-section, everything is exactly the same, only we have this distributed load of 12 kilonewtons per meter along element number 2. Again, our stiffness matrices are going to be exactly the same. We're going to calculate that. It's going to be exactly the same as before. Our global problem assembly, all the same up to this point here. The only time it gets different is having to calculate this distributed load. So the distributed load on element number 2 can be converted into nodal values. So using our equation here. So basically we have our 12,000 times the length of the element, which is 1, divided by 2 gives us 6,000. 12,000 times 1 squared divided by 12 is minus 1,000, and so on. So that's our force on element number 2. We have this 12,000 distributed load is equivalent to 6,000 on this point plus a moment of minus 1,000, minus 6,000 deflection here, force, and plus a 1,000 moment there. So notice those two moments are acting in the opposite direction, and that's because we want to cause this kind of U shape happening here. So we have a negative moment acting here, which is clockwise, and we have a positive moment, which is anti-clockwise there. So again, that's that negative and positive, and these are just shear forces. So again, just to reiterate, 12,000 Newton meters gets transformed into 6,000 newtons on each of the nodes, plus a moment of 1000 on each of the nodes acting in opposite directions. So if we look at our global force vector then, so that was just that only happens on element number 2. Element number 1 has no load on it. So nodes 1 and 2 have 0 load. So this is our force vector in this case. We can go ahead and form our global problem equation. In this case, it looks like this. And we can go ahead and we can solve that and we get a slightly different answer. Okay, so again, there's our deflection. So remember, that's the last time it was 0.01. So this is much smaller. It's about 1/3 of what it was. And the bending moment, again, can be calculated in the usual manner. In this case, we get 3,000 and 6,000. We can work out the same in our other element. We get 5,000 and 1,000. And again, our shear forces go to be 9,000 and 6,000. So again, let's just jump over to Workbench and have a look and see what our Workbench FEA model predicts. So again, I have the same model as we had before, only this time, if you look here, I've suppressed the force and the moment, and I've added in a line pressure. Okay, so we have the line pressure acting in there. If I take a look at that, we can see it's minus 12,000 newtons per meter. Okay, so again, if I click on static structure, you can see all of the loads and boundary conditions. So we have the fixed support here, remote displacement there, just allowing rotation, and I have a line pressure on this line here. So again, if I can look at my directional deformation on the Y, I can get a probe in there and take a look at that. So I'm getting minus 4.4 e to the minus 3. And again, I'll just go and look at the shear moment diagram because that has everything on it for me. So I'm getting, let's look at deflection first of all, 4.4 e to the minus 3. And if we go and look at our hand calc example, so we got 0.00375. So instead of 4, we're getting 375. So we're not too far off. Then in terms of bending moment, we're getting 3,000, 6,000, and 1,000. So again, here you can see I have 3,000, 6,000, and again going down here to practically 0. So I'm a little bit off down there. And our shear force is going from roughly 9,000 to 6,000. So if we take a look at what we had in terms of shear force, we had 9,000 and 6,000. So again, that's quite close to what we had in our Workbench model. Okay, so the next thing we're going to look at then is frames. So frames contain structural members that behave like beams, except that axial loads and deformations are also considered. So essentially we're talking about having the behavior of a beam element and a truss element in the one element. So in this case we have two displacements and a rotational deformation at each node. So if we take a look at our frame element, we're allowed to, this node is able to move in the X and the Y direction, giving us U and V displacements, but it also can change its slope. So we also have this rotation. So the displacement vector for this element is ui vi theta I, uj vj theta j. So it's got 6 degrees of freedom. We can proceed in a similar manner to that we used with the 2D truss, and we can use a local coordinate system. So if we define a local coordinate system x dash and y dash with direction cosines L and M, so that x dash is orientated along the length of the element. So again, we did this with the two-dimensional truss. We're just going to define a local coordinate system along the length of the element. Okay, and so its x dash will be along there, its y dash will be perpendicular to the element, and its theta will just still be the rotation of the element or change in slope. So in this case, we're going to have u dash is equal to ui dash, vi dash, theta I dash, and so on. Okay, so again, we have the same thing as kind of like we had in the two-dimensional and three-dimensional truss. We've got a displacement vector in global coordinates and one in local coordinates. What the important thing to note here is that theta I is actually the same as theta I dash, because the change in slope is the change in slope. It doesn't really matter which coordinate system you're looking at it in. So that's kind of a convenient thing that helps us out, that we don't need to transform between those two because they're exactly the same, but we do need to transform between ui and ui dash and vi dash and so on. So as we did previously, we can relate displacements in the local coordinate system to displacements in the global coordinate system via a transformation matrix. So we get u dash is equal to L times u. So that's the local coordinate system and the global coordinate system, and L is the transformation matrix. So in this case, the transformation matrix looks like this. So we have L, M, minus M, L, and the 1 here is because, as I said, if you look at that, if you look at multiplying this out, you're basically relating theta dash to theta. And remember, we said they're the same thing, so that's why the 1 is just there. Okay, so we've got the L and M relating U dash and V dash and U and V together, the 1 relating the thetas together, and then the same thing happening again down here. So here's our transformation matrix. So consider displacements then in the local coordinate system. V dash I, theta dash I, V dash J, and theta dash J are essentially one-dimensional beam degrees of freedom, and U dash I and U dash J are essentially 1D truss element displacements. So essentially, because we've already worked out the stiffness matrices for the one-dimensional truss and the beam, we can put those together to give the element stiffness matrix in the local coordinates for a frame element. So in this case, for a frame element, it's like this. So again, if you look at these ones here, these are the beam ones, and these are the truss ones. So if you remember, the truss was EA over L, 1 minus 1 minus 1 and 1. Okay, that's those in there. And if I go back and look at the beam element, I'll see I have these ones here from the beam element. We have the 4 by 4 from the beam. Okay, so there it is in local coordinates. So I can get that then in global coordinates by doing the usual thing, by looking at the strain energy and saying that if I have K dash, which is the matrix I just shown there, if I pre and post multiply it by L, I will get the global stiffness matrix. That allows me to conveniently get the global stiffness matrix. So we're using exactly the same methodology here that we used with the 2 and 3 dimensional truss. Again, we can work out the distributed loads using the local coordinate system as well. So if we do that, the distributed load in the local coordinate system will look like this. And essentially, these 4 elements are just the same 4 that we would have used for the beam from previously. And then the element distributed loads vector in global coordinates is just that multiplied by the transformation matrix. And we can further extend this then to 3D frame elements should we want. So that's just a kind of an introduction into frame elements. So essentially, we're going to reuse what we used with truss elements and beam elements, combine the 2 of them together, which gives us a frame element. Okay, so that is more or less all we want to cover with beams today. What did we do today? We looked at an introduction to beams and beam problems. We did the finite element formulation of beam elements. We looked at beam FEA examples. We looked at one with point loads, and we looked at one with distributed loads. And finally, we looked at the finite element formulation of frame elements. So again, as usual, everything I'm covering here is covered in much more detail in the book, so I do encourage you to get a copy of the book if you're finding this information useful. Again, the book is available from Amazon and all good book suppliers. And so with that, I will see you in the next video.